First, I would like to tell you that I was at the Santa Fe Institute where I studied complexity research 4 years ago, and it was a very exciting time. I met Stuart Kaufman and other distinguished researchers over there, and since that time I'm trying to study complexity here in Finland too, but it hasn't been too successful. Although a year ago we wrote an introductory book for complexity in organizations with Eve and Mika Aaltonen and me, and then we had the honor to have Stuart Kaufman as writing the foreword, which was very, very nice of him. And we had also, a year ago, we had a seminar with the Stuart here in Helsinki by telephone seminar, and it had a wonderful discussion with Stuart, and I think that was one of the prompts that actually made us to want this seminar here too, and Eve was very happy to cooperate there. So how do we see futures research is actually a kind of a collection or an integration of several more or less conventional research areas of the disciplines that we already are familiar with, and we can see that the futures research covers different areas, but its main point is actually in integrating those data, information and knowledge that is brought by other sciences, but of course it has its own paradigm and its own methodology as well. We can also look at it like this. So we have futures research and complexity research that actually are kind of multidisciplinary sciences, and what is common to them is the phenomenon orientation, which means that they study phenomena which are multidimensional, multifaceted, multi this and that. So in order to create insight of what is happening in that particular phenomenon. And we can share that actually in 3 different under sciences or sub-sciences. That everybody knows about impact assessment studies. That is something that we are doing, especially in the environmental research nowadays. And we have multi-stakeholder studies, which is typical for all collaborative projects and operations in the society. And then we have the interdisciplinarity, which is it's a part or a sub-area of multidisciplinarity. Now I just listed some of these kind of a family of phenomenon-oriented sciences. You see on the left there, you can see that complexity research, impact research, multi-stakeholder studies, multidisciplinary research and futures research are quite as sort of a complementing studies, complementing approaches to complex phenomena. And what is, as you can see, some of them have some very common approaches, but they also have their own characteristics and their system image and their application domains and application systems. Now I will briefly go into these that I have underlined here, some of these issues that are common to several multidimensional studies, like for example complexity research and futures research especially. If you take very briefly what futures research epistemology is about, it is that you can think that there are actually 2 ways of approaching data, information and knowledge. Is the acquisition and creation of new data, information and knowledge, and on the other hand reassessing and reprocessing existing knowledge. Now they have quite different methodologies that are needed for these 2. And then of course we have to recognize that there are variations of knowledge, that there are so many different types of knowledge, just explicit knowledge, tacit knowledge and so on and so forth, that we have to deal with. And if we take a short list of the futures research methods, you can see that there are Some of them are, of course, very familiar to you, but if it's not, I can just show you what are common to complexity research, soft systems thinking, for example, and also participatory action research, which can be used in social contexts. Alternative futures images creation, that is something that is done in complexity research as well. And, for example, the heterarchy processes are very important in complexity research. This is something that the Santa Fe Institute has been working with quite a lot, is with the heterarchy, which is the opposite to hierarchy. That means that there is actually no hierarchy in the conventional sense in many of the common organizational changes that we are facing today. And these are some of the methodologies that can be used in heterarchy processes. Another point that can be taken here too is how futures research is approaching the joint interest area. Now, this is the typical to multi-stakeholder studies, that you have different kind of stakeholders or disciplines like here that have a joint area, a joint interest area. And then when you approach the area, you come from the different angle, different understanding, different scientific culture into the joint interest area, and then you have to create a common language and common understanding of what is our joint interest. It can be a very small area really, but it is the one that we can start with, because that is something that we share. And once we have done that, we have agreed that this is something that we both share, then we can go along our own paths again. And what happens in practice is that you go back and forth in this, so it creates a kind of hypercycle of understanding and interaction processes. I have also tried to put in one picture what futures research tries to incorporate. Of course, the main thing is the multidisciplinarity and multi-stakeholderity. What a terrible word, actually. But you see that this is kind of like a rope maker. The rope maker has different strings that he or she is trying to put together and make a rope which is solid. So that's why the multi is so important to us. And what is happening there is, of course, that we understand that we are in a socially in a very strong transition period, and that's why we need new modeling all the time. And what are the sort of the slogans or the buzzwords? Or it's, of course, the holism and the heterarchy, the hypercycle, and the humanism. Well, humanism is probably a very common approach to all sciences. I would hope so anyway. But because of the H language, I thought it was nice to put it here. Nice. What we are now facing actually with the ubiquitous telecommunications all around the world and global telecommunication is that we have a lot of pieces of information, a lot of small pieces like in a mosaic. So I think a mosaic is a good metaphor for networked knowledge, that because we are collecting these little pieces of information, and then when and if we can put them together in a sensitive and in an insightful way, then we get a picture. You know, in English language there's a get the picture, also a question like that, and that's exactly what it's all about. Now, if you look at this metaphor, I think one of the important points is also the scaling. You know, if you go very close to this picture, so close that you put your nose on it, then you can only see one little piece. Now, if you try to judge the whole image only because of the knowledge of that one little piece, you'll be misled. Certainly, you'll be astray. But when you go further away, you get more pieces, and you get more pieces. Then you start to understand what kind of an image is going to emerge from that, and you create insight, in a sense, to the little pieces of information that you have. Now this, for example, is a good example of the networking today. The internet looks like this if we put the web caches in one picture, and this also gives you a kind of understanding that this is not as nice picture as the one before. So the networks create a much more distorted picture than the nice mosaic. What this picture illustrates nicely is that there are well-connected nodes and which have many connections, and then there are some who have very little connections. For example, here, these nodes over there, and these are then the links that connect the nodes. And the red ones here are the Amazon nodes, the Amazon mirror sites. Now, what you can study over this kind of network is that how robust it is, how well it can adapt to omitting or if you destroy some of these red points here over here, what happens to the actual network. Now, the studies show that Barabasi and others have done that you only have to take a couple of these red spots, a couple of these Amazon dots away, then you cripple the network very easily. So it's important when you build networks, and important when you build information networks and any kind of social networks as well, is to realize how vulnerable or unrobust a system can be if you have to if you destroy a well-connected node like this one over here, you destroy the whole area of the connections that are connected to that. If you destroy one of over here or over there, nothing much happens. So this is the kind of indication to how important it is to how you build networks. If it cannot be a random thing, if it would be completely random, it would be easier to cope with and easier to control. But when it is not a random network, like social networks are never random. There are many, if these nodes are people, they are well-connected people. Let's say, for example, if there is a known pop singer, I'm sure that there's a lot of people who know him or her, and then you can build a network over that information. And if that person is taken away, the other people don't have any connection at all. So this is another example of how the internet has been studied, to show you how different networks are and how different. This one is more robust in the sense that there are so many well-connected nodes that it's not easy to destroy that altogether. If you just take away a couple of nodes from here or there, then it doesn't destroy the whole picture. These are country codes for different colors. Germany, Italy, Japan, Sweden, UK, US, and so on and so forth. Just to show you how the networks of today are. Another type of network is this one. It was how numerous data packets were sent from one computer to many others. So these networks give you the idea that there are some very simple rules actually governing the connectedness and the actual nodes and how the overall picture is quite similar, although it can be any kind of network, and also the links and the nodes can be very different origin. Another very peculiar one is the one which is also made of internet connections. Just to show you one example. This is another example of social networks. This is probably image of social links in Canberra, Australia. Now you see, and now we are in the network actually seeing how these people interconnect with other people, so it's very intricate indeed. And other type that is used very much in disease control, for example, is how a contagion spreads quickly through a human network. It can be anything. It can be a disease, it can be an idea, it can be innovation, it can be virus. And this is particularly important to know for the people who control that, how connected people are. If you take this person away from spreading the disease, it's very, very good for the whole network. If you only take one of these persons, let's say put in a jail or hospital, it doesn't very much affect the whole picture. So this is also something that the disease control people are very interested in. And now say something about the self-organizing. This is a famous example of the Sandpile example that Per Bach, who was one of the pioneers of complexity research, wrote in, made this kind of experiment in IBM while maybe 20 or 15 years ago, where this was the setting was so that there was a place where a little plate, that there was sand grain by grain coming down to a plate, and then they made observation what happens to that sand pile. And they found out that there are critical thresholds when the pile starts to collapse, and there will be avalanches of different sizes. And the same continues on and on. And the more you put grains on it, the avalanche starts after a certain threshold, and then after the avalanche, then again it has time and space to mount to the critical threshold again, thus giving the understanding of how a kind of energy dissipation system works. And this understanding is used much in earthquake research, because the same happens in earthquake. Actually, the nature is full of this kind of self-organized criticality processes. Now, perhaps you are all familiar with Mandelbrot Fractal, which is one of the most beautiful things that computers have created, one would say. This is typically also a model that can be used, for example, in nature and other complex phenomena. Now, what we are actually facing today is that we have a lot of new integrative sciences, a lot of new sciences that are new in the sense that they are not the ones that conventionally we have had, but are a kind of integrative and new in between the conventional paradigms, connecting. So they are actually in the area of the joint interest of this particular neighboring sciences. So I just wanted to show you how there's an institute for the future in the US that has made this kind of new world map, and it shows you how different new sciences have approached to material sciences, biology sciences, energy and information sciences, thus filling the whole world, the whole area, the whole space actually, what can be done in connecting different and old scientific paradigms. And also, what is the situation today? You can see that there are a lot of emphasis on new technologies. Actually, these are the dates or the years that we can await new breakthrough in science on these fields. And as you can see, in between material, information, biology and energy, you have a new scientific paradigms, which, for example, many of these, like bioinformatics, are familiar to Santa Fe Institute. And this gives you the idea that we are really in a very confusing and mosaic type world, and to bring out some insight from this is a very challenging job, and we need complexity and research and complexity approach in order to make any sense on the world that we live today. That was my presentation. Thank you very much.